the lecture in business intelligence. Today is 3rd of April 2025. We are going to continue heute with our examples of deep learning by hand. Basically here you're learning how to perform deep learning in the basics, okay? So later on we will go on and we will deepen our knowledge in more applied manner, but these are the basics. I think it's important to know the basics before going deeper. So we have an example today. We're going to do 2 examples, okay? But will be very detailed, so I hope you like it. So the example 3 is a 3-layer perceptron with a forward pass. Okay, so we have now we have 3 layers. The last example we had 2 layers only. Now we have 1 hidden layer. So we have here 1 input vector of 3 elements. Then we have 1 hidden layer here with 4 elements. And we have 1 output vector with 2 elements. Okay. And we have a weight matrix which is representing the relationships between all the nodes to each other. So our first weight matrix has a dimension of 4 by 3. Okay, so this is the weight matrix. Put it here, weight matrix 1 to H, and this is going to be the weight matrix H to 2, and this has 4 by 2 elements. So each line is 1 element in the matrix. Okay, so the dimensions of the matrix 1H are 3 by 4 because we have here we have 3 elements, and here we have 4 elements, and the dimensions of the matrix H to 2 is going to have 4 by 2 because here we have 4 elements again, and in the other one we have 2 elements. So, is this correct? Do you understand? Any questions? You can give me a sign. Cool. Okay. Very good. Thank you. So let's do the example with real numbers, and then with that we can have a better feeling that we understand it. So as I said, you are doing now deep learning, so this is really important hot shit. I guess it's something that is really relevant for, and I will definitely ask about this in the exam in some form or the other. So this is the vector as we had the other day, x1, x2, x3, okay. Then we have our weight matrix. Here something like this. Takes a little bit of time to make it pretty, but I think it's worth it because it's more didactic. Please have patience with me. I like it when it's pretty. So, as we said, our first weight matrix is going to be 3 by 4, so 3 by 4, okay. So this is going to be our weight matrix. And then we have our bias as usual, okay. So let's fill it with numbers. This could be any numbers, okay. 1, 1, 0, 0, 0, 1, 1, 1, and 1, 0, 1, -2. So the bias, of course, has dimensions 1 by 4. So otherwise we don't, we cannot multiply and add up and stuff. And okay, so this is the first one, and the second, the weight matrix H2 has dimensions 4 by 2. So this is going to be something like this. And remember, we are only doing the forward pass, okay? So this is just simple as a pimple. So we have 4 by 2, so so this is the weight matrix to H22, sorry, H22, and we have this here, and 4 by 2. Okay, so we fill it with numbers again. 1, 1, -1, 0, and 0. The bias vector is going to be 1 by 2, and 0, 0, 1, -1, 1. Okay, so that's cool. All right, so let's hit the trail. Now we want to perform our feed forward pass, which is as simple as doing this. Oh wait, let me write this somewhere else. So we want to perform the feed forward pass. Yeah. And in order to do that, what we do is we just go ahead and say, all right, feed forward. And from 1 to H. So basically this step, okay, from 1 to H. What do? What we have done already, okay? So there is no rocket science here. It's multiplying 1 by 2 plus minus 1 plus 1 times 1 plus 1 times 3 and adding 5 and adding minus 5, I guess. So we go ahead and say 2 times 1 plus 1 times minus 1 plus 3 times 1 plus minus 5. And doing this you can do with your head, okay? So again, 2 times 1, 1 times minus 1, 3 times 1 plus minus 5. All right? And then the next one, 2 times 1 plus 1 times 1 plus 3 times 0 plus 0 equal 3. And 2 times 0 plus 1 times 1 plus 3 times 1 plus 1 equal 5. And 2 times 1 plus 1.0 plus 3 times 1 plus minus 2 equal 3. So you cool? Yes, everybody, yes. This is just like multiplying numbers, okay? This is all it's about. So what we do is we take this minus 1 and plug it in here, minus 1. And we have done already the work. So 3, 5, and 3. All right, so we just take these little fuckers here and then we put them out there. Right? So you cool? Then we go and we just go ahead and apply ReLU. Our rectifier linear unit function, which is like the activation function we're using. This is like our standard, okay? There are others, but we use that one. It's easy to compute and it's fun. Whatever is negative becomes 0, whatever is positive stays. So this is the output that we expect from H. If we got here, we get that. All right? Give me thumbs up, thumbs down. You can also give me hearts, you can give me fire, you can give me whatever you want, okay? Just joking. All right. And then, and this is new, okay, from last week. We just take the We just take the full output of h, and then we plug it into our next layer. Okay, so we basically do the feed forward again between h and 2. Okay, so we do the second step, feed forward between h and 2. All right, what do? We multiply 0 times 1, 3 times 1, plus 5 times minus 1, plus 3 times 0. Okay, so 0 times 1 plus 3 times 1 plus 5 times minus 1 plus 3 times 0 plus 0 equal minus 2. We plug that minus 2 here. And then again, 0 times 0 plus 3 times 0 plus 5 times 1 plus 3 times minus 1 plus 1 equal 3. All right. So we have done the feed forward pass here, right? Then we go ahead and we apply ReLU, rectifier linear unit. Whatever is negative becomes 0, whatever is positive stays the same. So what about that, guys? Isn't that cool? So this is y1 with a hat, y2 with a hat, and we have our feed forward pass. Deep learning is easy, okay? You just need one thing. You just need discipline to do it and over and over and over and over and over again until you just get it in your brains, okay? But this thing is easy. I think it's easy. It's just multiplying and adding numbers. Just need to know what to multiply. So, irgendwelche Fragen, auch gerne auf Deutsch. Any questions? Any questions? No? Ja, bitte. Nee, die Zahlen, du meinst diese, so, our friend is asking, how do I get to these numbers, okay? Is that what you're asking, right? This vector? This one? Yeah, these numbers I'm giving you, I can write any numbers I want to. Ich kann dir egal welche Zahlen geben, okay? This is some input I give you. Okay? So, die Zahlen sind irgendwelche Zahlen. Das ist jetzt nichts. Ich hätte da was anderes machen können. Ist egal. Okay? Wichtig ist hier die Rechnung. Jo. Alright. Gut, dann we are done with our first example today, and we go ahead and we say, okay, we are going to use, in the next example, we're going to use the feed forward and the back propagation. And for that, we need at the last layer of our architecture, we need a decision layer, okay? This is what we call a decision layer. Decision, I don't know if it's with one S or with two. Layer. Let me check. I don't want to write it wrong. I guess it's with one S. Decision layer. Okay. So the decision layer has the property that transforms the output Y with a hut into a set of probabilities. So what we have is a probability distribution function. In German, Wahrscheinlichkeitsdistribution, okay? So the probability distribution function has the property that all elements of the probability distribution function add up to 1, okay? Because the total probability is 1. And for this reason, we take our softmax function when applied to a vector x. It has the elements x1 divided by the sum of all vector elements, xn divided by the sum of all vector elements. You can say, oh my God, again with math, this guy is impossible. Okay, so this is very easy. Let me do an example, okay? Imagine we have a vector given by the elements 3. I guess we need to say this is the absolute value, okay? 3, -7, and 4. So the elements of the applying softmax to this vector are 3, absolute value here. So 3 plus 7 plus 4, 7, 3 plus 7 plus 4, and 4, 3 plus 7 plus 4. So everything is turned out positive. And then we have 3 divided by 14, 7 divided by 14, and 4 divided by 14. Okay. So if we do that in our heads, this is going to be here is 0.5, and then that's going to be a 0.15, I guess, and 0.35. All right. So that's our decision layer. That's what we do to decide. Is that cool? Again, just adding numbers, not rocket science, not doing nothing like super difficult, okay? And then we are ready now to explore like the real shit, I guess. Okay, so this is the ultimate example we will see in this, what we've been preparing for. Okay, so sample number 4 is a perceptron with 2 hidden layers with feed forward and back propagation. Okay, the layers are, I have a structure of 3 layers input, 4 and 2 neurons in the hidden layers, and then a 3 layers output. All right. So the feed forward is something that we have done already here, and I will go a little bit faster now on the feed forward part, because we want to focus on the back propagation. Okay, so let's paint the thing, the architecture. X1, X2, X3. Then we have our H1. Let me zoom it a bit. H1. This is our first healing layer. We have our connections there. So it's a fully connected architecture. This is going to be our weight matrix 1 to H1, these connections. Then we go ahead and then we paint our H2. Again, a fully connected thing. Fully connected means all neurons are connected to all other neurons, and that's weight H1 to H2. And then we have an output vector, let's say 1, 2, and 3 again, which is going to be our output layer. Okay, so this is that we will call this layer 3, I guess. Layer 2, layer 3, doesn't matter. Okay. And this is the weight matrix. No, we call this layer 3. We don't call it layer 3. We call this the weight matrix H2, 2, 3. Okay? So all these lines putting together the neurons are numbers, are weights, which is pretty much the same as we've been doing so far. So now we need to put some numbers again for you, for this, our friend who asked before. These numbers are just some numbers. Okay, I just write them out, but they're not really relevant. There could be other numbers. Okay, so imagine this is 2, 1, and 3. This is our input vector. Then we have a weight matrix right there. I need to leave some space in between. You will see later on why. So we have our weight matrix right there. Weight 1H1 and the bias 1. Let's put the, again, I'm sorry it takes a little bit, but it's from a didactic point of view stronger if we take some time to describe things neatly. Yeah, so we go ahead and say, all right, then let's let's put some numbers right there. 1, minus 1, 1, minus 5, 1, 1, 0, 0, and then 0, 1, 1, 1, just the same numbers as above. Okay, it's 1, 0, 1, minus 2. Then we go ahead and say, all right, then let's get another layer here. I need to leave some space in between. You will say, as I said later on, you will see later on why. So I put that right there, and then we go ahead and we get our numbers in place. So this is going to be the weight, I guess, H1, H2 matrix, and this is going to be the bias 2. We will put some lines in there as well to make it neat. We can duplicate the line, and yeah, again, it takes some time, but it's prettier. And if it's pretty, it's easy to learn. So 1, minus 1, 1, 0, 0, and then 0, 1, minus 1, 1, 3. All right? So we have, right now we have this fellow in place. We have this fellow in place. Okay? And we want to have also the next guy, which is it's going to be weight matrix for It's going to be a 3 by 3. Okay, so I need to put it, I guess, somewhere here. Okay. And then this is like 3 by 3 with the weights and the bias. So this is a weight matrix H2 by 3. And we put some numbers in there. Is 2, 0, -1, 0, 2, 5, and 1, 1, 1. This is the bias number 3. Okay, I forgot to say that our expectation vector, so this is going to be like y1, y2, y3 with the hat, and our expectation vector is 0, 1, and 0. All right, so at some point here I want to calculate an error. And this is going to be our y 0, 1, 0. This is what I would give you in the exam. Okay? Whatever is in black, I would give this would be the input for you to do the exercise. Is that understandable? Yes, everybody, yes. Leon, Nina, Hanefi, Yumana. Good. All right, then let's hit the trail, okay? Let's do first the feed forward, which is something that you should be able to do without, like, we have done it already like 4 times, so let's do the feed forward here. Okay. So I'll do the feed forward calculations here, down here. Okay, feed forward. You can scroll up and down later. Feed forward. Let's call it x to h1. Okay. So you can say it's 2 times 1. Just like we did above. Okay, it's just the same thing. 1 times -1 plus 3 times 1 plus -5 equal -1. So it's like 2 times 1 plus 1 times -1 plus 3 times 1 plus -5. And this delivers here at -1. All right, it's the same thing as we did earlier in the lecture today. Second is 2 times 1 again, plus 1 times 1 plus 3 times 1 plus 1 equal 5. So 2 times 1, 1 times 1, 3 times 0 plus 0. Wait. Am I correct here? No, I didn't write it correctly. I did the third, not the second. Wait. I just jumped one line. So this is 2 times 1 plus 1 times 1 plus 3 times 0 plus 0 equals 3. This is correct. Okay, so this equals 3. The next one is going to be equal 5. So 2 times 0 plus 1 times 1 plus 3 times 1 plus 1 is going to be equal 5. And then 2 times 1 plus 1 times 0 plus 3 times 1 minus 2. 2 times 1 plus 1 times 0 plus 3 times 1 plus minus 2 equal 3. So it's going to be equal 3. Good. This is something that we have already done. Then we apply ReLU. Zero because it's negative and the rest stays the same. All right. Any questions? No questions? Well, then let's do the feed forward pass, H1 to H2. We are here, okay? We did this, now we are here. Okay. What do? We take this, 0 times 1 plus 3 times minus 1, 5 times 1 plus 3 times 0 plus 0. Okay, but not really rocket science. 0 times 1 plus 3 times minus 1 plus 5 times 1 plus 3 times 0 plus 0 equal 2. Alrighty. We put a 2 right there. Next one, 0 times 0 plus 3 times 1 plus 5 times minus 1 plus 3 times 1 plus 3 equals 4. All right, then we equal it 4. What we did is 0 times 0 plus 3 times 1 plus 5 times minus 1 plus 3 times 1 plus 3. Okay, so we apply ReLU. And what we get is, what we get is the same because both are positive, so nothing changes. So same, but it's just the same shit. We are repeating The feed forward is always the same thing. And then we get the feed forward from H2 to our layer 3, I guess, Y3 we called it. And what we do is we take 2 times 2 plus 4 times 0 minus 1, okay? Just like that. All right, then we do that. 2 times 2 plus 4 times 0 plus minus 1. It's going to deliver a 3. All right. So, and then 2 times 0 plus 4 times 2 plus minus 5 will be a 3. Another 3, and the next one is going to be a 2 times 1 plus 4 times 1 plus 1, going to be a 7. All right. So you guys are with me, or you are already gone looking at your phone? Be with me. Give me hearts, give me fire. Okay, this is really hot shit, because you're learning deep learning, which is the backbone of all artificial intelligence algorithms, most that we see today in the industry. Okay, so this is deep learning, doing it with your pen and paper. So this is the last layer, and this is what we now do new. Okay, this is the new part. Yeah. Wait. Yeah, it's a 5 plus 5. Yeah, you're right. Is it minus 5? No, I want it to be a minus 5. Yeah, I changed this, okay? But thank you. I want it to be a minus 5. I want it to be a 3. All right, so now we go ahead and we apply, because this is the last layer, we apply a softmax. Okay, so how do we apply the softmax? We apply the softmax to our vector 337. All right, so we say this is going to be 3 divided by 3 plus 3 plus 7, 3 divided by 3 plus 3 plus 7, and 7 divided by 3 plus 3 plus 7. Okay? So if we do that, it's 0.23, 0.23, and 0.54. This is the second step. We're still in the feed forward, but we apply a softmax. So when applying the softmax, we get special numbers, so not really natural numbers. So 0.23, we get real numbers. So 0.23, 0.54. And this is our output. after applying the softmax. This is the output of our layer. That cool? All right, so what do we do now? We say, okay, we want to subtract our expectation to our and this will give us an error. Okay, this will give us an error. And our error vector is going to be (0.23 minus 0 is 0.23). So we just say 0.23 minus 0. Okay, 0.23 minus 0. 0.23. 0.23 minus 1 is minus 0.77. And 0.54 minus 0 is 0.54. All right. So this is what we called error of the layer 3. We have performed a full forward pass. Okay? A full forward pass. Any questions? Bitte. Ja. Nein, musst du nicht Relu machen. Man macht Relu nur in den intermediate layers. You need to do Relu only in the intermediate layers. In the last one, you decide, okay? And this decision is based on probability theory. After the softmax, you can test if these numbers add up to 1. Okay? Very good question. All right, so now it starts the fun part. Okay. So now you need to be really on top of it, like white on rice. So make sure you put your telephones away, because this is really fun, but you need to be alert, okay? You need to be concentrated on the shit. Otherwise, you will get lost, because this is a lot of numbers back and forth, okay? So please be into it. Concentrate. The back propagation starts, we take this error, okay? And we're gonna compute the error back, okay? Until we get a weight update. Is that cool? So now we start the back propagation. I will use this new color for the back propagation. The third step is the back prop. Okay, and so for the back propagation, we need to do some steps. The first step is going to be called 3A. Okay, make sure you stay with me. We transpose the error vector as new bias. Okay, so the step number 3A is going to be take this vector, take the error vector, transpose it and put it as a new bias. So our new bias B3, let's say B3 star, if you wish, is going to be this error vector transposed 3.A. So I'll just copy it, okay? Just transposed 0.23 minus 0.77, 0.54. Transpose it is when we talk about vectors, it's just we rotate it, okay? Just like rotate it. It's called transposed in math. All right? Is this step understandable? Everybody's saying yes. All right, then we go on to the next step. And the next step is something new. It's called dot product. Dot product. Okay, so do not be scared. It's math, but it's super easy, okay? So we do something called dot product of the transposed vector, error, the bias, and the output of the previous layer. So let me paint my superhero H4 here to explain the difference between dot product and scalar product of vectors. Okay, so this is my superhero, you know him already. Okay, super H4. So when you do scalar product, of two vectors, v1 and v2, what you do is you take the module of v1, take the module of v2, multiply them, and then the cosinus of the alpha is what you get. Okay, so basically what we're doing here is we are shading, putting the shade of the one vector into the other. Okay, so we're calculating a scalar. But when we do the dot product, we do something different, and we do this in deep learning because it's useful to extract features. If the vector 1 has coordinates x1, y1, and x2, y2, what we do is we get a new vector x1 times x2, y1 times y2. Okay, so this is the dot product. Dot to dot, coordinate by coordinate. All right. So we do the dot product here. And you will see this is super easy. It's easier than we have done before. So do not be fooled by the names. Most of the time people give smart names to silly things, okay? So what we do here is, stay with me, do not go. We multiply 2 by 0.23 and we get 0.46. 2 by 0.77 in minus and we get minus 154. 2 by 0.54 and we get 108. And so on. So 0.92 minus 3, 0.8 and 2.16. So again, the dot product, I'll do it here again. Dot product I'll copy it again, okay. 2 and 4, and then here I had 0.23 minus 0.77 and 0.54. The dot product of this can be done like 2 times 0.23 is 0.46. 2 times minus 0.77, which is minus 1.54. I'll do it here. 2 times minus 0.77, which is minus 1.54. And 108, which is 2 times 0.54. And then 4 times 0.23, which is, what do we say, 0.92. This is 4 times minus 0.77, which is going to be minus 3.08. And 4 times 0.54, which is going to be 2.16. All right. So you cool with the dot product? Yes, 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 yes. Somebody has questions. If you have any questions, wenn ihr Fragen habt, jederzeit, okay, es kann nicht sein, dass ich das alles so erkläre, dass keine Fragen hat. So, bitte, hilf mir, okay? This here is the step. Ja, bitte. Wo hast du eine Frage? Am Ende, ganz am Ende. Ja, weil wir nur den Forward Pass gemacht haben. Nee, man nutzt es erst am Ende, wenn ich den Backpropagation Schritt machen will. Erst am Ende. Okay? Ja, bitte. So, so das ist unser this is our new weight matrix. We are updating, no, sorry, this is our new, this is our new weight matrix. We are updating the weight matrix. So in the first feed forward pass, we had this weight matrix. In the next we're going to have this weight matrix. We are updating the weights. I'm going to whisper, we are learning. Okay? We update the weights, so we learn. We adapt. This is deep learning. Adapting the weights to something that we want to learn. Okay? Is that cool? So the third step in the backpropagation steps is third step is going to be like this. I'll paint it in green. We multiply the transposed error with the weight matrix of the current layer. Okay, we get the new error. This way, we get the new error of the layer above. So, in order to do so, we take the bias, the new bias, B3 star, and we multiply it by our weight matrix. So what we do is we take 0.23 times 2 minus 0.77 times 0, 0.54 times 1. I write it here, 0.23 times 2 plus minus 0.77 times 0 plus 0.54 times 1. This goes and delivers 1. The next one, 0.23 times 0 plus minus 0.77 times 2 plus 0.54 times 1. This delivers a minus 1. And this is the error 2. Okay, and this is the step number 3C. Okay. Any questions? Hello? Good. Then the next steps are just repeating the same. So I'll be a little bit faster here. Okay. So we take our error, and then we put it right there, and this is going to be our new bias, just the same step as before, 1 minus 1. Then we perform a dot product, here, so this is 0 times 1 is 0, 0, 3 minus 3, 5 minus 5, and 3 minus 3. Okay, so this is our new weight matrix, W H1 H2 star. This is the update. This is the update of this. And then again, we go and say, okay, this needs to be multiplied by the old weights to get the results. So suck, suck, suck. And then we get here 1 times 1 minus 1 times 0 gives 1. 1 times minus 1 minus 1 times minus 1 is minus 2. 1 times 1 minus 1 times minus 1 is going to be plus 2. And the last one is minus 1. So this is going to be our error 1. We take it up again. In the transpose form here, okay, so this 1 minus 2, 2 minus 1. And then again, we do the thing with our dot product, and then we're done. Okay, so we do that. Just perform the dot product, which is going to be like 2 minus 4, 4 minus 2, 1 minus 2, 2 minus 1, 3 minus 6, 6 minus 3. And this is going to be our bias 1 star, and this is going to be our new weight matrix. And we have done our backpropagation, motherfuckers. Now you know how to do deep learning. Okay? So, jetzt seid ihr in der Lage, die Basics von Deep Learning selber mit einem Stück Bleistift durchzuführen. Okay? Das ist etwas, was viele Leute nicht können. Das Deep Learning machen mit dem Rechner. Mittlerweile kann man halt ein Programm fahren, bitte mach mir das, und spuckt einen schlauen Code. Aber das hier ist die Basic. Und das ist wertvoll. Okay? So, auf einmal bin ich weg. Mein Video ist nicht so, die Verbindung scheint nicht so stabil zu sein. So, Fragen bitte. Ja. Mhm. Nee, wir wissen, dass es zwei Elemente haben wird, weil das hier ist ein Vektor und du hast hier 2, 1 und 2. Wir wissen, dass es 2 Elemente haben wird, weil wir hier 2 Elemente haben. In der nächsten hat es 4 Elemente, deshalb hat es 4 Elemente, weißt du? Ja, und hier hat der Error 3 Elemente, weil wir da 3 Elemente haben und so weiter. Der Error ist wie soll ich sagen, wie etwas, was übrig bleibt nach der Berechnung, muss genauso viele Elemente haben wie dein Output. Okay? Wir hatten hier 2 Elemente, haben wir hier auch 2 Elemente. Es ist eine gute Frage, die man sich stellen sollte, auf jeden Fall. Und ich hoffe, das macht jetzt Sinn, okay? Passt es? Ja? Okay, cool, super. Weitere Fragen? Ja? Auf Deutsch, mein Gott, weiß ich nicht. Aber du bist halt auch in Google mächtig. Dot product in German. Ja. Tüpfelchen, Pünktchen Product, Tupfen Product. Die Bezeichnung in Englisch ist Dot Product. Vielleicht ist die Übersetzung in Deutsch anders. Warte mal kurz. Scalar Product in German. Ja, der übersetzt das genauso. Bitte bleibe nicht bei den Namen, okay? Also hier ist die Mathe wichtig. Bei dem was ich jetzt Scalar Product genannt habe, nimmst du die 2 Vektoren und du projizierst eine in dem anderen. Okay? Und das ist das eine Modul mal das nächste Modul macht das Cosinus. Das ist die reine Physik davon. Bei dem Dot Product, was wir hier machen jetzt im Sinne von Weight Update, okay, ist, ich multipliziere die einzelnen Elementen 1 bei 1, okay, 1 zu 1. Okay. Ja, gut, die Vorlesung ist in Englisch, deshalb muss ich es in Englisch erklären. Aber meine Erfahrung ist, oder ich interpretiere es so, Mathe ist eine Sprache und in Bayern wird nicht genau so gesprochen wie in Hamburg. Verstehst du, wie ich meine? So, jeder macht so ein bisschen anders. Wichtig ist das Konzept. Aber der Bayer spricht genauso gut wie der Hamburger, nur ein bisschen anders halt. Ja. Weitere Fragen? Gut, dann nehmen wir, also das ist natürlich nur den ersten Forward Pass. Wir nehmen jetzt die neue Weights und wir müssen es nochmal machen. 2, 1, 3. Das ist jetzt der Weight, also der Input, das bleibt unverändert. Und der neue Weight Matrix ist dann 2, 1, 3, 1, minus 4, minus 2, minus 6, minus 2, 4, 2, 6, 2, 2, minus 1, 3, minus 1. Das sind die Zahlen, die wir gerade ermittelt haben. Hier, bam. Okay? Nur gedreht, damit die grafische Darstellung stimmt. So, wenn wir denn, das ist B1 Stern, wenn wir jetzt das Ganze multiplizieren, dann kommen wir in einem Feed-Forward auf 15 minus 30, 30, 11. Okay, wenn wir Relu anwenden, kommen wir auf 15, 0, 30, 11. Okay. Dann nehmen wir die nächste, WH1, H2 Star, war 0, 3, 5, 3, 1, 0, minus 3, minus 5, minus 3, minus 1. Wenn ihr das Ganze multipliziert, dann kommen wir auf 184, minus 184. Und nach Relu-Anwendung kommen wir auf 184, 0. Okay? Und so weiter. Die ganze Kiste wird einfach weitergemacht. Wir machen hier WH2.3 Star, 0.46, I'm sorry, I changed to German, 0.92, 0.23, I just don't notice. My brain is just fucked up. Sorry about that. So minus 1.54, minus 3.08, minus 0.77, 108, 216, and 0.54. We multiply feed forward, and that should be 84, 87. Minus 284.13 and 199.26. So we do that. We apply our soft max, and what we get is 0.15, 0.5, 0.35. We subtract the new weights, and what we get is 0.15 minus 0.5, 0.35, which is our new error 3. And then we do the back propagation again, back and forth, and then it's just forever and ever. Okay, so basically what we're doing here is we're going back, forward, and back many times in what we call, this is a forward pass, this is a backward pass, and what we do is we do that in many epochs, many iterations. Okay, adjusting the weights, and to adjust the weight of a neural network is to learn. Okay, this is what we do here. We are learning. Good. Questions? Any questions? So, no questions. I'll stop the video here.